All right, this is dealing with your one-dimensional beam equation and the finite element. And there was an added section that I put on the Google Drive. Let me show you how to get to it. If you go to my website, go on down to classes, and go over to the Google Drive, then our course, and then projects 2, 3, 4, and okay, apparently, let's try that again. Okay, so if you go down to the very bottom, you will find some notes here. If you look at Dr. Reddy's books as well as the handout, you'll notice that the shape functions that are in finite elements can represent no more than a third order. So here he has y is equal to y1 plus theta 1 plus the rest of this based upon that drawing. Now, let me show you where his handout is. If you look at it, you will see, okay, wait a minute. Okay, here's his handout. If you look at this equation, 23, the solution is capable of producing is third order. So here's his example. This is fine until you notice when you get in here and look at a simple uniform load on a cantilever beam, you'll see the exact solution has an x squared over in here and an x squared here, meaning it's fourth order. And as a result, a 1D solution to a uniformly distributed load is not exact. So there's no real way to get the exact solution out of this. So the question is, and by the way, this is the same with the 2-dimension and the 3-dimension. It's impossible to get an exact solution. The question then remains, what do you do next? So, and in essence, this term right here, this fourth order term, is not in our solution or in our assumption of the solution. So what do you do? Let's take an example and we'll find out what you can do. Let's see. We're going to take just a cantilevered beam. Just one beam. And we're going to go and look at his solution. Now, I wrote it in here, but I'm going to draw it back up. He had wx squared, so I'm going to try to move this down and copy this as well. Wx squared over what I remember to be 24EIL, but that might be wrong. Was it 24? Then 2L squared minus something in there. Two L minus X. And it's squared. So this is supposed to be the exact solution to Here. Yeah, I have to take that out. This is supposed to be, here, this is supposed to be the exact solution to a simple cantilevered beam. Now we're going to solve this in a second. Here, I don't like the way this looks either. It looks ugly. So here's my beam. Goes out. Has a uniform load on it. So I'm going to actually solve this. So I'm going to need to figure out L. I'm going to need to figure out EI, or I might as well split them. I'm going to figure out E. I'll take it to be 1,000. I'll say I is equal to 2, just so I can keep some. And I need my load. How about just 10? I'll make my length of my beam 20. So your first inclination may be to go out into the finite element code and put node 1, node 2, and say this would be element 1. And then take all this information and put it in. And what we'll do real quick here, I have SignLab brought up here. So I'm going to go in here, and here I'm going to do a clear, and I clear the screen. And then I'm going to put in L is equal to 20. I'm going to put E is equal to 1,000. I'm going to put I is equal to 2, and W is equal to 10. Now what I'm going to do is I'm pretty sure, and you're pretty sure as well, that the maximum deflection is going to occur right over here at the end. So I'm just going to figure out what that is. If you put in X equal to L, your deflection is going to be that L squared over 24 EI L. Then you're going to put in 2L minus L squared. So this term will drop out an L, so you'll have 2L. This term, like I said, would be L squared, because 2L minus L is just L. Then you got 2L minus L squared. In my case, or better yet, why don't we plot the exact solution? That may be the best thing to do. So let's go in and take our code, and to do this, I'm going to have to drop this video and go to the other machine. So what you're going to see is another video that follows straight after this one that deals with this. So with this, I'll stop this video and go to the other computer and run it.